Hello everyone. A very happy morning to all. It is my great pleasure in welcoming you all for this online webinar session organized by the Department of Mechanical Engineering. I am Ram Kumar, Assistant Professor in the department, and I would like to share a brief profile of our college with all of you. Francis Xavier Engineering College is located at the heart of Tirunelveli city in the state of Tamil Nadu, and it was established in the year 2000 with a vision to provide education in engineering with excellence and ethics to reach the unreached. Our Francis Xavier Engineering College comes under the SCAD group of institutions. Our institution has been offered with autonomous status for a period of 10 years with effect from 2019. It has also been awarded gold category by AICTE CII survey and industry linked technical institute in the year 2018. We offer 6 UG programs, 10 PG programs, and more than 400 students are pursuing their degrees in our campus. The Department of Mechanical Engineering is the largest department in the campus with 600 plus students and 30 plus faculty members. Our department has been supported with good infrastructure and excellent lab facilities. We offer BE in Mechanical Engineering and ME in Industry Safety Engineering. The UG program is accredited by the National Board of Accreditation. Apart from regular academic activities, our students have been trained and imparted with the various skill training programs and value-added courses. The special feature of our department is establishment of 3 applied laboratories in addition to the regular labs. The purpose of this applied lab is to inculcate the students with innovative skills which is required by the industry. The well-defined objectives of our department with its collaborative teamwork enables each and every student to march towards the college vision. With this introduction, I once again welcome all the viewers for the session and hope we will have a productive time. Thank you.
Dear faculty members and all participants, my warm welcome to all of you. It is my great privilege to introduce our resource person, Dr. J.V. Murugalal Jayan. Currently, he is working as advisor and a research analyst aerospace in Lovely Professional University, Punjab, and also working as Chartered Engineers Aerospace Division, IE, Mumbai. He has completed BE Mechanical Engineering in MS University at 2004 and ME Aeronautical Engineering in Anna University, Chennai at 2006 and completed his PhD in PU University at 2014. He has totally 14 years experience in teaching, industries and R&D academics. He served 10 years of head of aviation studies in various universities. He is the life member of International Association of Engineering and Technology for Skill Development, Aeronautical Society of India, the Indian Science Congress Association, the Institute of Engineers, International Academy of Science and Engineering for Development. He has published more than 60 international journal publications and published in international conferences. 10 PhD scholars are pursuing their PhD under his guidance. He has been honored by getting Young Researcher Award and Rashtriya Gaurav Award. Now I invite such a wonderful personality to take this session. Welcome you, sir.
Hello, good morning. Hope plenty of researchers might be watching this session, that current trends in aerospace industry. So, in our research, we are having plenty of platforms, plenty of labs, in the sense hyperdynamics, superconductivity. Plenty of researchers are there. So today we'll be focusing on these 3 areas: future and superconductivity concept in aerospace, our research on blunt body, what we do in blunt body, hypo and hyperflow instruments. So before I enter into my actual session, I would like to tell which are the companies we are associated and which are the my major areas we are working with: high-speed aerodynamics, flight instrumentation, logistics, internal testing. These are the major areas we are covering, and now we are associated with Attack and Pinnacle majorly, And Spain, Edivon, we are working with Edivon research facilities. These are the areas mainly we are working with. Before entering into this, diving deep into these three concepts, I would like to give you some entertain over what actually research, and very few minutes. I'll give you a very few minutes. What actually research and where we do mistakes. Normally, when all we guys are crazy in doing research, but where we do mistakes. So plagiarism, this is what the major issue which affects internally, in the sense research internally and external research, which may suppress you to come out of the bound. In fact, there are some parameters which force you to, or which may induce you to create plagiarism. So out of this, I would like to mention only three major issues. This lack of knowledge, in the sense, not in the sense of theoretical or practical knowledge. I am coming to the lack of knowledge about actually what research is. People, you may have an idea that research, in the sense you have to innovate something, or you have to cultivate something new, or it should be a pattern given, or it should be a pattern given. That is what that actual problem with you. No, that is that you have to cross from that boundary. And the second is laziness. Once you look into all these research facilities and these hurdles, you will back. That's the another parameter which force you to do plagiarism. And third one is pressure to publish. Nowadays in schools, colleges, and even in industry, it's they are very deeply they are troubling, pressurizing to publish research papers. So these are the parameters forcing you, and then there are two types of plagiarism. One, intentional plagiarism. Intentional plagiarism, it is actually easier than stopping the unintentional plagiarism, in the sense you actually doesn't know that you are repeating a work. So that will be overcome only through research or literature reviews. Got it? Only through literature reviews you can overcome that unintentional plagiarism, because you actually doesn't know that you are plagiarizing. And what could be research? What you can do with research? You can categorize, describe, explain, compare, correlate, predict, control, deliver. All these categories comes under research. Why I'm giving all this stuff in the points, in the sense you should be aware that research is not something you are innovating. Something pattern is not research. Error is also a research. Wherein the future researchers, they will come forward and say, okay, this is an error statement. We should not go in. It will help them in that way. Error is also a research. Basic, applied, and quantitative. I hope you might be aware of this. Basic, theoretical format. Applied might be implemented is somewhere in industry flow chain somewhere. Quantitative, numerical areas. These are all the types of research you could do. Now I'll jump into our point, that is our research on superconductivity. This is one of our slab what we are doing. So today I'll be discussing only, I am not going to explain you something theoretical or what. I'm really explaining to you what we do in our facility. What we do in our facility, that may be informative for you. So you might be spending time in focusing on objectives, title fixing, guide fixing. You might be spending time on that. So this information may help you some actual problems. One second, technical error. Thank you. So our first lab is superconductivity concept. Here in, say this. So look at here. One second. Look at here. So screen. Look at here, distribution and generation. These two are evenly calculated and smart gridded. In fact, say we are having plenty of thermal power plants, plenty of power plants we do have, and we won't generate overload, because energy, there is a problem. For the problem we are facing is storage. I will come to, you may having some doubt that we are having batteries, all the stuff. I will come to that point. But if we could able to generate 1000 megawatt, that 1000 megawatt has to be utilized somewhere. So with that is why we are using all these smart grids. In fact, that is why we are using all these smart grids. So if we couldn't able to utilize that load, we have to stop the generation. Power generation has to be stopped. So here in the storage concept, comes into the picture. So now almost all countries, particularly German, they are vast advanced than Indians. They are working towards this storage concept in a very big way. So now challenges what we face in smart grids, power cuts, voltage fluctuation, and major area is this energy storage limitations. This is what the major area we are actually facing trouble in this scenario. So now economic losses. So this is what one survey what we did couple of years back. Sorry, maybe around 3-4 years back. This is one survey. So actually we consider only few industries. We didn't dive deep into aviation industry or aerospace industry. So later on we went into aerospace industry too. I will come to that point. So wherein we could able to understand the losses is around few millions, and the others you can see $220 billion. You can imagine how much loss we could. 1 second. $220 billion. You can imagine what might be the losses we could able to understand, and we could we could able to found that storage was the essential problem behind this smart grid or the power generation and utility. In between these two guys, with the actual vital phenomena which is playing is storage. Again, in storage also plenty of resources are going on, such as synthetic natural gases, hydrogen, batteries, lithium batteries. You may think you can see here, it is already in the deployment stage, and this is actually in the commercial stage. But these guys are still in research, this many concepts. You may please take a screenshot of this. This will help you for the upcoming researchers who could able to work with superconductivity. They can, and we speak majorly this because this is a system wherein we can store plenty of energy with a small device. If we could able to develop something with this superconducting magnet, if we could able to develop this, that will be helpful for the society. And this is not only in India, plenty of researchers are doing in this area, SMES concept. And so again, technological gap, again what we could in structural accept, cooling response, and magnetic, all the four areas we could able to find the technological gap. The structural stability in terms of how could we able to eliminate these vibrations, and in maintaining low temperature, that was a very difficult task. Throughout our literature review, these are all the areas you can actually work out in superconductivity. This cooling property, how could be done, and the time required and response, those areas, and investigation required for uniform magnetic fields. These are the four major areas actually we need research in the field of superconductivities. So young researchers, it will help you and directly giving you the four major points which you could work on: that elimination of vibration, cooling. Plenty of researches are going on this, and response parameters, and even in magnet, how we could able to create a uniform magnetic field. Is it possible? There are plenty of simulation. Of course, we have to agree that we don't have experimental facilities in India. We don't have experimental facilities in India, but simulation facilities we do have, and plenty of simulations are going on in plenty of universities. And what motivated us to do the first thing, already we could able to find a very big research gap. So there are some fundamental gap is there which we could able to play with. That is the first accept. And the second target, this voltage fluctuation and power cuts problems with society is facing. Not only so don't take this in terms of only with the public or domestic utilization. You have to virtually imagine, virtually take in the sense of aerospace industry, propulsion, everywhere. Energy storage, if it is possible, that will help you. Moreover, every year, so this area will help you. I would like to give you a fantastic information that DST and government funding every year around 5 to 6 crores they are spending only for energy storage and materials for energy storage. Look at this. Every year they are spending. So if you could able to come out with excellent proposal that will help you. Kindly note down all this information. This will help you. And in our research, our major objective was, as I discussed before, this stress and strain analysis and cooling could be possible or what, and how this HTS tape configuration insulator can be given, how much thickness insulator, how much layer we have to give. This area we have worked out, and uniformity in energy storage estimation and uniformity in magnetic field transfer. These are all the four major areas which we are working on with respect to the gap what we could able to found structure. Kindly note down, you can also work in this area. We are having plenty of results. We could able to produce plenty of results. Cooling area, and major issue is this magnetic. Now mechanical research methodology, what we have configured a magnet, HTS tape, that is insulator system, and SME structure, how much turns or how much coil we have to give. That is what, how much coils we can give, how much gap we can give. That is what the simulation we work with. And stress strain analysis in field of mechanical. And in research methodology, what we use with thermal is, first we studied on cryocooling and the selection of coolant and cryocooling technology and thermal analysis. These are the four parts what we did under the thermal wing. So there are actually four wings: mechanical, thermal, electrical, and magnetic. In mechanical, I already explained which are the area we work with, and in thermal, which are the area we are working with. I already. And in electrical, the insulation part, ACDC continued unit, and electrical losses has to be investigated. So these are the four major areas which we are doing with electrical part. And in the same thing, the magnetic critical current and the magnetic field availability to do work with. These are the areas we are doing simulation, what we did and what we are doing in magnetic area. And of course, initiative taken, social applicability. It is not limited. Still, there are plenty of social applicability is there. It is not limited, but I'm giving you a small glance on this. And other application: space propulsion, ship propulsion, defense, and aviation. Aviation sector is purely depending on depending, and they are having a very big wing for research in energy storage nowadays. Out of limitation of time and out of limitation of our company profile, I couldn't able to give all the results, but I could able to give some of the results research what we done so far. Mechanical, we actually designed a comparison at 77 Kelvin, Kelvin and 14 Kelvin. What we did is, and the length of superconductivity matching with the literature. This is what the accuracy used with analytical correlation and the length of the superconductivity matching with the literature. Got it? Our prediction, first we did our prediction whether it is matching with any of the literature. That is what we did initially, and it's matching. And then we can see a present model reproduce the previous result with minor errors, which may be because of our operating facilities or of our operating system mesh sensitivity, maybe because of mesh sensitivity. But in fact, it is actually matching with our result. The old results is also matching with our results. And AC losses we could able to find, and energy storage estimation for 77 which we could able to find. And thermal, we are actually, one second, there's my pointer. Look at this. We don't have that much difference between the prospect which is existing and what we did, and there was a very small change which we could able to find, and these are all the variation what we could able to find in our results, and what we used is console for this. And in thermal area, we have worked with silver, and I would like to give you one information: the best superconductivity is gold, but economically it is not feasible. That is why that is what the research is going on. So economically feasible material, if any one of our researchers could able to produce for the public or the industrial society, that will be a great achievement, because very few people used to work with superconductivity. And in magnetic area, we actually played with these turns and you can see this gap. This is what we played with, and we increases and decreases this number of these turns and this gap. And I hope you are watching and it is you could able to understand. So you can even play with this number of turns and this gap and even the coils. You can also come out with plenty of research and analysis by using these methods. And in electrical part, we actually will pancake coil method. We look at this. So look at this. We went for this type of coil methods, and this is what the or dismantle how it looked like. So arrangements of coils for SMES, what we use this type of arrangements. And electrical here also we could able to gap the tapings. We could able to find the effect of gap among the layers. We have found the effect of number of turns. If we play with number of turns, what actually happen? If we play with this gap, what actually happens? These are all the results we could able to find. And look at this, AC losses was also found increasing with number of turns. This was one of the major findings in our research, that AC losses are found to increase with number of turns. Out of all this plant, it took around few years, and we could able to find these terms. So critical current and magnetic flux density, how it transfers, gap, how it is dropping down. So we have to take a balance on these two things. And these are all the outcomes we could able to produce. Less superconductivity required for 14 Kelvin temperature, and AC losses found to increase with the number of turns, and single peg coil and double peg coil have been evaluated, and and electrical resistance influence the computational time. So these are the four major outcomes we could able to come out with our research what we did for around 2-3 years. So this may be useful for you, young researchers, because you don't want to do this simulation again, because already we could able to give you results. And these are the outcomes. Discuss research progress and materials today. Elsevier. I kindly take a screenshot of this. These papers will help you if you are really interested in this superconductivity area. And these are all for electric propulsion. We could able to give some solutions, and kindly note down all these papers. These are all our research outcome. Around 1720 plus Scopex index and SCA papers we could able to publish for the society during this period. And now we will jump into the second part of research on blunt body. Before that, I would like to tell you about hyposonic and hypersonic. Hyposonic is a technical term which we use for subsonic regions. Low subsonic layer, what we use is hyposonic. It's a technical term, and hypersonic is beyond Mach number 10, 11, 12, 14, all those stuff what we call as hypersonic. And even hyper velocity flow regions is also there. As you researchers, you might be knowing, and you can fill with QAs, I can explain you. Now I will jump into the blunt body concept. Why we want to go for blunt body? Say, I hope it is visible. If you consider this as a conical probe or a re-entry vehicle or an object, whatever. Say if it travels at subsonic level, okay, it won't. This shock wave is not going to affect this body. So if it crosses, if it keep on crossing, if you are keep on increasing this velocity of this object, this shock wave initially come here, then it will get attached. Once it get attached, this space get closer to the body, and what will happen, because this once this space comes close to the body, this shock layer, this normal shock layer, then it will be bow shock, then it is attached shock, then this guy plays as a radiating shock layer, in the sense it absorbs heat and there is no gap to exhaust it. So what it will do, it will reflect, it will hit this shock layer and it again hits the body. So more strong shock around the body, and this aerodynamic heating calculation and efficiency of outcome So these are all the parameters we have to optimize. So we have to play with the blunt body, we have to play with the velocity, and we have to play with the altitude, and how the layer reacts at say escape velocity, those layers, how it reacts, and once it crosses troposphere, how it is going to react. So we have planned to come out with a coupled equation which could be useful for the society, wherein for all these parameters, body, velocity, and altitude, if we could able to sync all this and give a common mathematical model, that will be helpful. That is what I have mentioned, this aerodynamic heating, more strong shock waves, more strong shock waves, heat calculation, and noise. We are plan we tried to optimize these 4 points in a generic equation. Our objective was, so for example, I would like to tell that Apollo 11, that recent few years back, it was actually once it crosses the escape velocity, you all know it should have this velocity. Imagine 10.67 kilometer per second. It will impact the region once it enters the earth surface, and it is not possible to open to deploy the parachute at that velocity. So what say, this object, it falls down at 10 kilometer per second, and we couldn't able to deploy the parachute even to reduce this. So what is the only source? Energy. We have to play with the energy. No other source, because engine is not there. Once the vehicle re-enter, engine power control is not there. Engines are not there. Only with the help of energy we are going to play. And what energy is available? Only kinetic energy. Kinetic energy and the flow field around the body. That is what the two things available. The flow field, again, the flow field, we have to control it. Heat energy plays a role. Got it? An object enters the earth. Once it enters the surface, the velocity will be very high, 10.67 kilometer per second, and there is no power plants or anything to be which we could control. The only option is parachute. At that velocity we can't open, and we can open only if it is 150 meter per second. Got it? So we, at this point we can play only with the energies. Energy has to be transformed somewhere, and we have to release the velocity. So this is, now hope you understood. And now the wonderful science come into the picture. Integration of science and engineering comes into the picture. So that's air molecules has will bounce off, and the only how we can play in this region is we have to play with shock waves. We have to play with this shock waves. So detaching the shock waves, giving them enough space so that the heat can be transferred somewhere. We have to give a gap so that this generated heat can travel somewhere. That is the only option. That is why we went into this research and gathering shock waves, how it can be done, and how this blunt shape can be largely played. These are all the areas we work. And this, like food chain, there is an aerospace chain. You can call this as aerofoil chain or aerospace chain. Look, initially Pushpaga Vimana, those people, right for this, they started with this rectangle shape. So what they found there are drag. Then we went to oh, this is the wonderful design for subsonic. That this shape, what we call is airfoil. Then we keep on increasing the velocity. We went for wedge, but the shock wave started formation, and it was attached, and it is not going to affect if it is within the limits. Okay, altitude limit, no issues. Then once we enter once we enter space, this gap plays a role. You can see this gap between this shock and the surface. This started playing the role. So now this generated heat, there is no way to escape. So it will hit back the object and it tends to damage the object. So again we went for this blunt body, so that we could able to detach the shock and we could able to create a space. But it is what is that? Speaking, it is very easy, but detaching this wave up to one extent, how we can enlarge it, what kind of angle we can give, it's a very big phenomenon which has to be done. Now these are all our research objective in this particular platform slab which we use, hypervelocity, validation of the existing literature, prediction of aerodynamic and various hypersonic velocity. These are other. So first we have planned, as I discussed earlier, one aerodynamic equation, generic equation, that is what the. So again, for initial stages, we try to create plenty of blunt bodies with the existing literature and with our own predictions. We could able to give some plenty of blunt bodies such as bicone, blunt cone, conic, blunt tangent olive, and olive methods. These are all the basic cones which we are working with. It is not limited. We are actually working with around 40 to 50 shapes and plenty of results. We could able to get thousands of results on this particular research. And in biocone, you can see the gap. You can see how it behaves, and here how it behaves. And here you look, it is not at all suitable because this shock, there is no space for the heat to escape. And of course, this is the tangent olive is okay, with okay. These are all the results which we could able to produce, and you can see the outcomes for the last 2 3 months, which we have produced the hypersonic vehicle aerodynamic shock prediction, all IOP series and material science engineering. We could able to produce this, and I won't recommend this. If you want, you can go through these first two journals and the third journal. This will help you. The fourth journal, we could, actually this is an error one, but still we published because it may help some students if they are going in wrong track. This particular paper will help them. And now we will jump into the third slab of our presentation, that is actually hyposonic and hypersonic flow instruments. Hyposonic and hypersonic flow instruments. So normally, say we'll consider in sports dynamics or sports aerodynamics, football, ratchet, cricket bat, stem, if you consider the sports, and if you go into the automobile front bonnet, backspace, the curvature, track, frontal velocity, and those things we use. If you go with aerospace, every inch by inch we will collect and gather this aerodynamic parameters over it. And for that, we have plenty of instruments, but still, and simulation parts are there. But still, we are not relying only on simulation. We do go for experimental study. For experimental study, as of now, we do have plenty of apparatus, and we are relying on internal experimental study. But in practical, plenty of colleges and universities, you might be having internals with you. But how much challenges you have faced to calibrate it? Normally, how we calibrate? You will go for repetitive, and you will lift this an x-axis or y-axis. You will confirm some curve or inverted C. You will get an inverted C. Okay, fine. It is done calibrated. Do you think it is calibrated? No. It is not even calibrated for 1%, and it should not be used for academic purpose. Academic purpose we are not supposed to use. We are not doing such calibration even. Calibration is a very big parameter. Before utilizing, let it be academic, let it be research, let it be industry, wherever you use, calibrate the apparatus very proper. The apparatus has to be calibrated at the right way and with the right sensitive instruments. But in practice, we have to agree the scenario going on in our academics. With the pita tip, we are calibrating around 70 meters per second. So that is our worst situation. Okay, fine. I don't want to go deep into this. So flow angularity plays a role. Tunnel blockage plays a role. Measurements, pressure distribution, boundary layers, thin layers, laminar layers, how it can be predicted. So what we have to do is, inch by inch, we have to find out how the flow parameter is throughout the test section. Test section, what we call is hard. So our objective was, if we could able to produce one instrument which can be utilized for hypo to hyper, plenty of optimization has to be done. Plenty of optimization has to be done. Because as we discussed earlier, this cone, say, let again I will take this as an example. If this cone decreases, we can go for higher velocity. But if this cone angle increases, our sensitivity of the reading what we got will be good. So we have to optimize these two parameters here. So if we go for low cone angle, we can go for any we can go for measuring high velocity flow. If we go for high cone angle, we will get a sensitivity reading. So we are in a position to optimize this wherein we could able to use at 2.5 mark, or from 0.1 to 2.5 mark. That is what we were doing. And this is what we discussed. Usually we go for normal beta tube and high efficiency probe for supersonic, and even we go for wedge, spear, maximum correlation, acceleration, plenty of. So what we have planned is we go for, why shouldn't we go for a 5 probe 20 taping or 25 taping, wherein we could able to graph it out, and we could give a grid calibration methodology to the society and to the academicians, so that the upcoming researchers, what they will do, they can they can predict what might be the velocity at that particular point, that will help them to move further for the next research. And this is what we planned is a subsonic level internal distribution for a different Mach number. Before jumping into this particular research, or before what is it, manufacturing, or before designing this particular instrument, we actually did a very excellent background work. Excellent background work. Yasphere, Clay Yasphere, pressure distribution, plenty of others, thousands of others. They come out with thousands of results and thousands of instruments. We could able to shortlist few of them which is relevant to our research, and we manufactured that. We experimented and we simulated, and we could able to come out with plenty of results. And these results, as of my suggestion, kindly take a note on this. This will help you if you are interested in this particular slab of research. And this 20-degree cone angle, this is actually semi cone angle, in the sense 40-degree cone will be best suited for up to 2.5 Mach, and few areas are detached. From here you can see, so you can see the shock angle will be 29.3 for 3 Mach number. So it will be well suited. So as per our research, in the upcoming slides, I will let you know how come it will be. So hope you understood. Again, I am repeating. Once the cone angle increases, the reading what we get will be excellent and sensitivity. Once the cone angle decreases, we can go for high velocities. So if you could able to play with these two parameters, I'm sure you can come out with plenty of results, and that will be helpful for the society, those who are working in this particular field. Slab. This is what I was discussing. Sensitivity increases with increase in cone angle. An example I have given for a creative example. You can read this and says a 60-degree up to what Mach number we can do. Where what is the shock angle? 40 degrees have been used, and why we can go. So this is one example that I could give you. Say this is one of the probe we could able to uh, realize, and very soon we are going to manufacture this. And three in the same thing, 3 probe we already manufactured. We had applied for patent also. And say, look at this. There are 5 holes actually. So total 25 holes, and you, at a time you will get a 25 points grid, and we could able to find around 1,000 grids inside the test section, and we can plot that in a polar curve, and that will that is actually giving enormous data for the researchers, those who are going to use that particular facility. Look at this. This is what we discussed, semi cone angle. And one more thing you should you should know. So let this be the surface. If you want to predict the flow somewhere here, that flow holes or the tapings should be perpendicular to the surface, not with the flow. So you should know this. Actually, you will get a confusion. This, say if you are going to use one conical probe, to measure a X or Y flow. Let it be viscous or viscous flow. That is not going to affect here. But this holes should be, this is a thumb rule, the hole should be perpendicular to the surface, not with the flow or parallel to the surface. Forget about the flow direction. That we can identify. Flow angularity can be identified. Look, this should be perpendicular. Got it? This flow taping, kindly look into my screen. This flow taping should be perpendicular. Hope you understood. And we played with different Mach number range 2, 3, 2.5, and we could able to find that we can go up to 2.5. So this is a wonderful results what we got. And then we went for three-dimensional meshing also, and there also in up to 2.5 Mach number it was excellent, and 1.2 Mach number was also excellent. And these are all the 3D sample results we got. We didn't stop with the research. We went for Yasphere with 2 holes, how it could work, and with 5 holes, how it is working. And we have actually manufactured, and we got experimental data also for this. If you are interested, write to us. We will give you the data if you are really interested in this research in this particular slab. And these are all the research outcome we could able to produce. And I'd like to give a sincere thanks to my research team. They have published more than 35 research articles, all of SCI and Scopus Impact articles in the last 1 year. And we have filed 3 copyrights, 2 books already be published in the field of renewable energy and current trends in aerospace. And 1 PhD already produced, he got awarded, and 2 patents we have applied. So these are, I'm giving a very small background of work what we are doing out of time limitations. Again, I will summarize the overall. I would like to summarize. So superconductivity area, that is an excellent area. If you are really interested in research, you can go for 4 major research gaps, or you can even work with play with all the 4 also: mechanical, electrical, thermal, and magnetic fields. So I have already given you what are the research gaps available, what are the fundings available for that particular slab, and you can, which are the vertical you can work with also. These are the 4 verticals you can work with in superconductivity. And in blunt body, how this airfoil chains plays the role, and for hypervelocity blunt body plays a role. And if you could able to give an generic mathematical model for all by optimizing 3 parameters: aerodynamic parameters, altitude, and velocity. And this aerodynamic heating, what we call is, the technical term is radiating shock layer. If you could play optimize with these 4 parameters, that is a good area of research. You can go on. And the third area is calibration instruments, wherein no we actually use the instrument, but no researchers are working with how to calibrate the instrument. Before using the instrument, that has to be calibrated. There I have given you a sensitive report where the cone angle plays a vital role with respect to the velocity, and the flow taping should be perpendicular to the surface. I hope I have given you enough information. And our other verticals of research are dynamic camber we are working, flow properties we are working, aerodynamic flutter we are working, UAV aerodynamics. Around 3 team is working on this. Nozzle expansion theory, hyperaerodynamics, aviation, human factors. We are associated with some aviation industry, in this airline industry, and we are working with this. And I would like to tell roughly 36 team members are there, and I would like to congrats and give my sincere thanks to all my teammates, students, B.Tech students, M.Tech students. 36 plus students are working under me in different slabs. Now, if you have any queries, kindly post on. I'm here to deliver you. Mr. Muthukumar.
Hello, thank you very much, sir, for your wonderful presentation.
Thank you.
There are many questions from our participant side, sir. Now I am
Please,
going.
please. I will be there for another 10 or 20 minutes.
Okay, sir. Okay.
I will try to clear all their queries in terms of current research and future research in the field of aerospace.
Okay, sir. Thank you, sir. I am going to ask you a few questions for them, sir. The first question is: majority of aerospace vehicles importing from other countries. Why can't we produce in India?
That is actually a wrong concept. First of all, I'd like to tell you, we actually we rely on media. Really, I'm telling you, we rely on media, and we know only actually, in fact,
Okay, sir.
we are exporting our researches also. We have a wonderful space industry, including DRDO, ISRO, and all, and plenty of scientists are working. And caliber products we are actually delivering, wherein we are actually bit big in engine, the power plant division, but actually we are working with different countries also. We are working with different countries also. Even in avionics also, we are actually strong. Our ADA is very much strong in avionics. We are actually supplying plenty of simulation instruments to other countries. That is the actual fact. Of course, we may not be a pioneer in aerospace, but we are also one among the pioneer in aerospace, I could like to tell.
Thank you, sir. Thank you for your explanation. The another question is: how are the aerodynamics theory used in aerospace engineering?
That is what I was discussing. Aerodynamics is the parameter. Once the flow, flow is there, aerodynamics there. Let me consider a kite. You consider one kite. If you want to flew the kite at some altitude, there is some technique we use to actually give vibrations. These are all actually impact with the kite and the air. That is actually aerodynamics. In aerospace industry, in all way, that is what I discussed. Elementary theory, radiating shock layers, bluff body shock layers, flow parameters, flow prospects, flutter, wing flutter, camber theory, everywhere in aerospace industry, aerodynamics we are using. Even from kite. If you consider one small kite, playing kite, or even a paper plane, there is aerodynamics is there. So first of all, we have to feel it. So if you prepare on paper aircraft and if you flew it, aerodynamics is there. The major phenomenon is flutter, radiating shock layer, nose cone, drag, lift. These are the 5 major areas wherein aerodynamics plays in aerospace industry. 5 major areas: flutter, drag, lift, aerodynamic parameters, and radiating shock layers. Got it? It is not limited.
Thank you, sir. The final questions from our participant. For simulation, do we use ANSYS software or any other, if you can suggest, sir?
What?
For simulation, do we use ANSYS software, one of the software, or any other?
I understood the question. Wherever I go, there will be a question like this. Actually, dear participant, this ANSYS, Nastron, MATLAB, COMSOL, all these stuffs are actually commercial software. So up to one extent you rely. If you are a research beginner, you rely on this commercial softwares. Once you cross that level, you try to generate your own codings and you try to generate your own mathematical model, what we are doing in our research. I have shown you very few research slides because we have some limitation wherein we couldn't able to give, because many things are under patent and under publication procedure. All are reputed journals too. So I couldn't able to give all the results. But my advice is, if you are a beginner, work with the commercial softwares. And if you come out from that vertical, if you are in the next slab, if you really want to prove yourself in research, go for your own coding, generate your own softwares. That will help you in big way. It is not that difficult task, but you have a team. You have a team, dedicated team, you can work, and I'm sure you can do it.
Okay, sir. Thank you for your clear explanation for the session, sir. Thank you.
Thank you very much.
Hello everyone. I believe that you all thoroughly enjoyed the session. This is Maheshwari, Assistant Professor in the Department of Mechanical Engineering. I would like to extend my sincere and deepest regards to the speaker, Dr. J.V. Murugulal Jayan, Advisor and Research Analyst, Lovely Professional University, Punjab, for the talk on advances and current trends in aerospace research with current samples. It was indeed a great opportunity to listen to Dr. J.V. Murugulal Jayan. The presentation was very well organized and the explanation was clear. We have students, faculty members and research scholars as participants, and I have no doubt that it reaches every one of us intensely. A sincere thanks goes to you, sir. I would like to thank all the participants for your wonderful participation and excellent cooperation. I thank you all. On behalf of the Department of Mechanical Engineering, the faculty, the students, and I extend my gratitude to the organizing team, the college management, key people of our institutions, and everyone activated with us. Thank you all.